Hello students, welcome to the class. So the chapter we are dealing with is modulation and demodulation, where we'll be studying about modulation. And in the modulation we have already studied about the AM, that is amplitude modulation. And in the amplitude modulation we have seen the waveform of the amplitude modulation. We have seen the total power in the AM wave, that is PT, in terms of PC and sideband powers, right? We have also performed a few numericals based on that. We have also derived the expression for VAM, that means instantaneous value, otherwise the voltage of AM wave. That expression we have seen. We have seen the modulation index in terms of Vmax and Vmin. We have also seen various waves of AM wave for different values of MA, where MA is equal to 0, 0.5, 1 and 1.5, right? So now in today's class we'll be seeing from the expression PT is equal to PC into 1 plus MA square by 2. Okay, so this is the expression, right? PT is equal to PC into 1 plus MA square by 2 is the expression. So we will see what is the value of PT if we substitute the value of MA as 1, that is 100% modulation, for the condition of 100% modulation. For 100% modulation. So if we just substitute the value of MA is equal to 1, we are going to get as PC into 1 plus 1 by 2. So 1 plus 0.5 is nothing but 1.5 of PC, where PT is the total power transmitted and DC is the carrier power. PT is the total transmitted power and PC is the carrier power. So with MA is equal to 1, okay, so with MA is equal to 1, the total power is 150% of PC. 150% of the PC. So compared to the PC, it is 150% more, the total power transmitted for the condition of MA is equal to 1, that is undistorted, for undistorted transmission. For undistorted transmission. That is for the condition of 100% modulation. Right? So what we have seen here, PT is 1.5 times of PC when we are considering the modulation to be 100% modulation. When we are considering the modulation to be 100% modulation, the total power transmitted is 1.5, otherwise 150% of that of PC. Okay, PC into 150%. In terms of percentage, if we express this, we can write it as 150% of PC. Right? So this is the total power in terms of carrier power with MA is equal to 1.5 times of PC. Right? Next. Now we will see the power in sidebands. What is the power present in the sidebands? After seeing the power in sidebands, we will see the efficiency. power in sidebands. So in the entire AM wave, from the total power PT, how much is present in the sidebands? Okay, and the sideband power is written as PSP, sideband power, PSP, and which is PLSP plus PUSP, that is power in the lower sideband and the power in the upper sideband. So this can be written as, how it can be written? MA square BC square by 8R. This we have already derived in the PT, and how we have taken the RMS values of the sidebands, we have taken this. Okay, so how to take the RMS values? The peak value is MA BC by 2, and whole divided by root 2 gives you the RMS value, and how it is calculated? Divided by R, square of it divided by R. Okay, so how it becomes now? This becomes MA square BC square divided by 4 into 2 into R. So that became MA square BC square by 8R. This is for one sideband. This is the power in one sideband. And we will consider the same for two sidebands. MA square BC square by 8R. Okay, which is nothing but twice of it. So we can simply write it as MA square BC square by 8R into 2. 2 times adding or multiplying into 2 means the same. So this is going to give you 4. So this can be written as, the expression in this form can be further written as MA square by 2 into MA square by 2 into BC square by 2R. Okay. So this can be further written as, what is this? MA square by 2 into BC square by 2R, where BC square by 2R is nothing but what? The PC value. How PC? Carrier power in the carrier PC is given as RMS value of its value, peak value. That is VC is the peak value divided by 22 whole square divided by R. That gives you BC square divided by 2R. This one. So this is nothing but PC. So substituting this PSP is equal to MA square by 2 into PC. So PSP is equal to MA square PC is equal to MA square PC divided by, this is the power in sideband. So how we have computed that? We have considered the power in the sideband. So power in the sidebands is calculated by VRMS square divided by R. So RMS value of the peak value of the sidebands has to be taken, and the peak value of the sidebands is given by what? MAVC by 2. So MAVC by 2 divided by root 2 whole square divided by R gives us MA square BC square by 8R. Okay. So this is the power in single sideband. This is the power in single sideband. And for two sidebands, we will just take another term. What LSB we have taken, we have to substitute the same value for USB also. Adding the two similar values or multiplying with 2 means the same. That's why multiplying it by 2 gives you 4R in the denominator. From this BC square divided by 2R is taken common because it is nothing but BC as I have written it there. Okay, so MA square divided by 2 into BC will be the final expression for power in sidebands. Okay. So if you remember this expression also, you can use in the calculations. If you remember, one of the one of the problem was asked to calculate the power in the sidebands, where we have done it by PT is equal to PC plus power in sideband PSB. So PSB is equal to PT minus PC we have done. Okay, if you want to directly perform it with this expression also, you can do it. That is MA square PC divided by 2 will be the expression for the power in sideband. Okay, total power in the both sidebands. Okay, again if it is to be calculated in one sideband, then again divided by 2 has to be done. That is divided by 4. MA square PC divided by 4 will be the power in single sideband. This is the total power in the sidebands, right? Next. Transmission efficiency. Transmission efficiency eta. So we are studying the transmission efficiency eta. Okay. The transmission efficiency is defined. Okay, so what is this transmission efficiency? Transmission efficiency basically gives you the idea of how much out of the power is useful power. Okay, the total transmitted power is not going to carry the entire information. The information is only contained in the sidebands. Carrier is simply of no use, otherwise simply the carrier is not having any information, right? So the transmission efficiency gives you an idea of out of the useful part in the transmitted power in terms of percentage, how much out of that is a useful part of the transmitted wave. So it is defined as, the transmission efficiency is defined as the ratio of the power having the information, right? That means power of sidebands, because the information is present in the sidebands, isn't it? Information is present in the sidebands. That's why it is the ratio of the power having the information, the amount of power that is having the information. Otherwise, the power of sidebands that contain information okay, to the total transmitted power. Because the information is only contained in the sideband, so it is the ratio of the power of the sidebands divided by the total power. So efficiency is given as power of sidebands by total power transmitted into 100%. This efficiency is represented in the form of percentage. Is PSB divided by PT. Okay, just now we have derived the expression for PSB, and that is MA square PC by 2, isn't it? Just now we have derived MA square PC by 2 divided by, what is PT? PC into 1 plus MA square by 2. PC and PC gets cancelled. Okay, so further this expression how it can be written? MA square by 2 divided by 2 MA square, 2 plus MA square by 2. Okay, so this can be written as MA square by 2 into 2 by 2 plus MA square. 2 and 2 gets cancelled. Okay, and finally the efficiency can be written as MA square by 2 plus MA square. MA square by 2 plus MA square. So this is about the efficiency. Okay, so this is about the efficiency. The transmission efficiency is defined as the ratio of power of the sidebands. That means the power of the actual information. Okay, the airwave where the actual information is contained to the total transmitted power. Ratio of the sideband power to the total transmitted power. Okay, so eta is given by PSB divided by PT, and PSB just now we have derived, just we substitute it there. By calculating or simplifying this, we get MA square by 2 divided by 2 plus MA square. So this 2 and 2 you can cancel out just here itself, and you will get it as MA square divided by 2 plus MA square is the final expression for eta, and which can be written in terms of percentage as MA square by 2 plus MA square into 100% into what? 100%. Okay. So this is about the efficiency. Transmission efficiency of AM wave. Next. So what is the expression for efficiency? MA square divided by 2 plus MA square into 100. Okay. Now we will see the efficiency for various values of MA. So here we consider first case. First case of MA is equal to 0. So in the efficiency expression we substitute 0 divided by 2 plus 0, which is 0 itself. So if MA is equal to 0, the efficiency of the transmitted AM wave is 0. This is the first case. So when MA itself is 0, then naturally it is an unmodulated carrier, and the unmodulated carriers are not having sidebands. When there is no sidebands, then there is no power in the sideband, and efficiency is the ratio of sideband power divided by the total transmitted power, and the sideband power is 0, so the total efficiency is going to be 0 itself. Now case 2, and we consider it to be 0.5. Consider it to be 0.5. So we substitute the value half by 2 plus half. Okay. This can be written as 1 by 2 into MA square. This is also MA square. 1 by 4 into 4 into 2 is 8 plus 1. This is going to be 4 by 9. 1 by 9, which is nothing but 0.1111 equal to 11.11% of efficiency. So for case 2, what we are considering? We are considering the value of modulation index to be 0.5, and this is 0.5 means nothing but half. So that gives you 1 by 9, and it is 0.111111. So that is going to give you 11.11%. So what does this mean? The efficiency means that out of the total transmitted power, 11.11% of the power is having actual information, and remaining part is simply of no use because it is just the carrier. Okay. With 0.5% of MA, the 11.11% of the total transmitted power only is having the information, and remaining part is completely of no use. Remaining part is just the carrier, which is having no information, and it is of no use. Right? Clear? Next about the case 3. NA is equal to 1. Eta is equal to MA square by 2 plus MA square. So this is nothing but 1 by 3. 1 square and 1 square, 1 divided by 2 plus 1, 1 by 3, which is nothing but 0.3333 into 100, 33.33%. Okay, this is efficiency. So when we consider the MA is equal to 1 for the case MA is equal to 1, that is perfect modulation, 100% modulation. For 100% modulation, the efficiency is the 33.33%. Okay, efficiency is 33.33%. The remaining 66.66% is simply of no use because it is just the carrier signal. Information is contained in only 33.33% of the total transmitted power. Information is contained in only 33.33% of the total power transmitted. Of the total power transmitted. Whereas remaining 66.66% contains carrier power and is of no use. It is of no use. 66.66%. Okay. So it is further this case also where information is contained in only 11.1. Information is contained in only 11.11% of total power. So out of the total power, only 11.11% is having the actual information. Okay, so this is about the efficiency for various values of MA. We have seen the efficiency for various values of MA, where for 0 it is 0% efficiency, where for 50% modulation, that is 0.5 as MA, it is 11.11, and whereas for 100% or perfect modulation, 53.33% of the total power transmitted. Where the information is contained only in the efficiency percentage. Percentage of efficiency is only having the information contained, right? Next topic, modulation by several modulating signals. Modulation by several modulating signals, and we are studying for AM, amplitude modulation. And here we have taken example of being one carrier signal and one modulating signal. The mixture, otherwise the combination of both gives an EM wave. This is what we have studied. But in actual use, the carrier wave will be amplitude modulated by several waves, several modulating waves. Okay. So when a carrier is amplitude modulated by several modulating signals having different peak amplitude values and frequencies. So all the modulating signals will be having different frequencies and different peak amplitude values. Okay. When they are amplitude, a single carrier is amplitude modulated by several modulating signals having different peak amplitude values and frequencies. The MA modulation index of the complex AMJ is given by MA total. MA is equal to root of MA1 square plus MA2 square plus MA3 square and so on MA n square. Okay, so the total MA, and it will be a complex AMA. So what they are saying, when a carrier is amplitude modulated by several modulating signals, that means several information signals having different peak amplitude values and different frequencies, of course, the MA, that means the modulation index of such complex AM wave, is given by the root of the sum of individual MA squares. The sum of individual MA squares and the root of total is the total, what you can say, modulation index. Total modulation index is given by the root of sum of the squares of the individual modulation indexes of each modulating signal. Okay, where the individual MA is Vm by Vc, where Vc is common for all the terms, but Vm definitely changes. Vm for all the signals change. Okay, so that results into different MAs, and the sum of the squares of the different MAs and the total root, and the root of that total is the total MA. That means modulation index of this complex AM wave. Okay, clear? Now, types of AM signals. Types of AM signals, or we can say forms, different forms of AM wave. You can also say it as different forms of AM wave. Okay. In the form of the transmission. So in the AM wave, we have seen that AM wave is having three terms or components. It is basically having three components. And three components are carrier, the lower sideband, and the upper sideband. The lower sideband and the upper sideband. So the AM wave is basically comprising of three parts, otherwise three terms or three components, where the first one is the carrier, the second one is the lower sideband and the upper sideband. Right? The information is contained in only the sidebands. Information is contained in only sidebands. That's why to improve the efficiency or to save the power that is transmitted, they come up with various forms of the AM wave, where it is called as single side band with full carrier. This is the first form, which is called as SSBFC, single sideband with full carrier, which is also called as the same concept with other name, with transmitted carrier. Ssp TC. Okay, single sideband. What does this mean? I will explain you. This is the first one. The second one, single sideband suppressed carrier. Carrier. SSB single sideband suppressed carrier. The third form is double sideband suppressed carrier. These are just the forms of transmission of the AM wave, just to save the transmission energy, otherwise transmitted power. DSP, double sideband suppressed carrier. Okay, so basically these two systems are single sideband systems, and this one is a double sideband system. Okay, these two are single sideband transmission systems. This is one double sideband transmission system, where in this a single sideband along with carrier is transmitted, and the other form is single sideband with no carrier, that means suppressed carrier. Whereas the third form is the double sideband suppressed carrier. Both the sidebands are transmitted, but the carrier is not transmitted. Okay, so we will study detail about this transmission form of AMs. So the first one, single sideband with transmitted carrier. Okay, so this can be represented as this is Ssp, this is Lsp. This is carrier. Sc means carrier. Okay, this is one form or. Fc, that is carrier, and the upper sideband. Okay, with this spectrum frequency. So in the frequency spectrum, we have seen the three terms as the carrier, and on the left hand side the lower sideband, on the right hand side the upper sideband. So in this system, single sideband transmitted carrier, the one sideband is suppressed. One sideband is suppressed and other sideband with the carrier, along with the carrier, is transmitted. Okay, so in this form of the sideband transmission of the AM wave, that is single sideband transmitted carrier, as you can see, either the lower sideband or the upper sideband. Okay, either the lower sideband or the upper sideband along with the carrier is transmitted. So in this both representation of the transmission, we can see common as Fc, that is the carrier. Carrier is present, carrier is transmitted. Out of these two sidebands, any one is transmitted. So that is what I have written here. One sideband is suppressed. One of the sideband will be suppressed and the other sideband with the carrier is transmitted. Okay, other sideband along with the carrier is transmitted. Okay, in this type of transmission, 1/6 of the transmitted power can be saved. Of transmitted power is saved. 1/6 of the transmitted power can be saved. Okay. So out of the total power transmitted PT, the total power 100% power is there. Out of which 1/6, okay, 1/6 of that can be saved. Amount of power can be saved. So this type of transmission is definitely going to improve the efficiency of the transmitted wave. Okay, as efficiency of the system can be improved. More power can be saved from the single sideband transmitted carrier system. Right? We see the next one now. The next form of transmission. So the next one, single sideband but suppressed carrier. Carrier will be suppressed. So carrier is also not transmitted. So how this type of transmission appear? Only lower sideband is transmitted, or only the upper sideband will be transmitted. Okay. Out of the two sidebands, either lower sideband or upper sideband will be transmitted. Of course, no carrier will be transmitted. Carrier is not at all transmitted, and out of these two sidebands, one of the sideband will be transmitted. Such system is called as what? SSB-SC. SSB-SC, single sideband suppressed carrier. Okay. So, carrier is not transmitted. Carrier is not transmitted. One out of the two sidebands. One out of the two sidebands is transmitted. One out of the two sidebands is transmitted. Okay. Lower sideband or upper sideband is transmitted. Carrier is not at all transmitted. Carrier is not transmitted. One out of the two sidebands is transmitted. Okay. So this type of transmission of AM wave is called as single sideband suppressed carrier. Carrier is suppressed. One of the sideband is suppressed, and only one sideband is transmitted. That is lower sideband or upper sideband. And this type of system 5/6 of the power or transmitted power can be saved. So this system can save 5/6 of the total transmitted power, okay, which is having. So as it will saving the highest power, it will be having the highest efficiency. So efficiency is definitely improved by this type of transmission. Okay. So what is this type of transmission? See, you cannot see the carrier signal here, and in this we cannot see the upper sideband, and here we cannot see the lower sideband, and we cannot see the carrier. Okay. So this is transmitting lower sideband, this is transmitting upper sideband. Right. So this is called as a single sideband suppressed carrier. Carrier is suppressed, carrier is not transmitted, and out of the two available sidebands, only one sideband is transmitted. Okay. Here. Next. Next one is the double sideband suppressed carrier. Of course, carrier is not transmitted, but both the sidebands will be transmitted. Double sideband suppressed carrier. DSPSC. Double sideband suppressed carrier. So how this appears now? Lower sideband and upper sideband. So here there is no case of or. Okay, because both the sidebands are transmitted, carrier is missing. Okay, carrier is missing. So carrier is suppressed, otherwise is not transmitted. Carrier is suppressed, both the sidebands are transmitted. Both the sidebands are transmitted. Both the sidebands are transmitted. So the signal will be a good quality signal, right? Apart from that, 2/3 of the total transmitted power can be saved. Okay, because most of the power is wasted in the carrier and carrier is not having any information present. So just by suppressing that carrier, we can save a lot of power. Okay, so this system saves 2/3 of the total transmitted power. Total transmitted power is saved. Right? 2/3 of the total transmitted power is saved by this system, that is double sideband suppressed carrier, DSP-SC. Okay. So these are the various forms of the AM wave when single sideband is transmitted along with the carrier and without carrier, single sideband with and without the carrier, and double sideband without carrier. Okay. These are the three forms in which we basically studied single sideband and double sideband. Now we will see the advantages of single sideband over double sideband. So Ssp transmission. Now we are going to see about the Ssp transmission, its advantages. So what are the advantages? Bandwidth is half. Is half compared to the double sideband. So bandwidth is half of that of the double sideband transmission. So with this, what happens? More stations can be accommodated by this system. Next, secrecy. Secrecy can be maintained. The secrecy of the signals. That means the signals can be more, what we can say, safe. Okay, over the transmission. Improved signal to noise ratio, that means SNR. Improved signal to noise ratio. Okay, so the signal to noise ratio is improved. Large efficiency. So what is efficiency? It is the ratio of sideband power divided by the total power. Here the total transmitted power itself is the sideband power, and the numerator is also sideband power, so it is going to be 100%. Okay, for single sideband suppressed carrier or double sideband suppressed carrier. If the carrier itself is removed, then efficiency is going to be definitely increased. Ideally, it can be 100%, but practically it cannot reach to 100%. Okay. No fading. The signal do not tend to fade. Fading of the signal, that means the reduction in the strength of the signal is avoided, can be avoided with the SSP, that means single sideband transmission. So the single sideband transmission is having bandwidth half of the DSP because only one sideband is transmitted and there two sidebands are transmitted. Secrecy can be maintained. Okay. Improved signal to noise ratio. Now, signal to noise ratio is also going to be improved. Large efficiency and no fading of the signal. That means reduction in the strength of the signal is not or can be avoided. Fading can be avoided. These are the advantages of SSB. Now we will see the disadvantages. Where in the disadvantages we can see extra circuitry is required for the suppression of the carrier, suppression of the other sideband, single sideband. So we have to suppress one of the sidebands, so that it makes disadvantages we are seeing now. The disadvantages say that the transmitter and receiver become complex and expensive. The transmitter and receiver circuits become complex and expensive as additional circuitry is to be added to perform the suppression of the carriers, right? Another disadvantage, not suitable for good quality signals like music and can be used only for speech signals. Okay, so it can be used in mobiles, it can be used in walkie-talkies. So wherever just the information is important, whereas the quality of the sound is not important, it can be applicable. Not suitable for good quality signals like music. Where in the music it is also becomes very vital or important to transmit the signal in the proper form with proper frequency, with proper processing. Okay, so in such applications it is not suitable, it is only suitable for the speech signals. That means just sending the sound signals over some medium. Right? Next, applications. It is used in mobile communication, it is used in police wireless communication, that means walkie-talkie for police wireless communication. It is used in military communication. And it is also used in point-to-point communication. It is also used in point-to-point communication, right? So it is used in mobile communication, where again the speech is only matters, the quality of the signal hardly matters. Police wireless communication in the walkie-talkies, where only passing the information is important and the quality of the sound is not going to play a very important role. Military communications from the base to the remote locations, otherwise some other locations for the communication of the soldiers. Point to point means shore to ship and ship to shore. In the we can say in that communication, where we need to communicate with the ships and the shore. There also it can be used in point to point communication. Right? So these are the applications of the different forms of AM. Right? So this is about the transmission of AMs, and in the next class we'll be seeing the AM modulator, how the modulation is performed, and AM transmitter. And these two topics will be the last topics in this chapter, that is modulation and this will be the end of the syllabus also, right? So in today's class we have discussed about the different forms of AM. The next two topics we will cover in the next class. Thank you.